Hello students, welcome to aimsindia online classes. This is a chemistry session. Here we are discussing about the chapter periodic classification. Yes, in the earlier sessions we have seen the classification of elements into different groups and blocks, all the concepts we have seen. Now based upon that periodic table, how the properties of the elements are being trending, how the properties of the elements are being changing from left to right in a period, on top to bottom in a group. Okay, that we say the trending of atomic properties in the modern periodic table, how these are trending, that we are going to see in this session. Especially we are going to say about atomic size. One of the properties of the elements is atomic size. So if we are able to understand the trending of atomic size or atomic radius of the atoms in the groups and periods in the modern periodic table, we can understand how the remaining properties are being trending, how the remaining properties are being changed, because mostly remaining all properties will be related to atomic size. So if we understand how this atomic size is changing, we can relate the remaining with this atomic size. So first let us see about the atomic size trending in the modern periodic table. Atomic size is defined in terms of atomic radius. Yes, the size of the atoms is considered in terms of their atomic radius. What is atomic radius? The atomic radius is defined as the distance between the nucleus and the valence shell of an atom. For example, if you consider this as an atom, they mentioned it as hydrogen atom. Now, if you say the distance from the nucleus of hydrogen atom to the outermost orbit of that hydrogen is taken as radius of that hydrogen atom. We can say atomic radius of hydrogen. We know hydrogen has only one shell with one electron. Now the distance between this one first shell and the nucleus is considered as atomic radius of hydrogen. Okay, in the same way, for the remaining elements also, they might have more than one shell. Out of those all, from the last shell, from the outermost shell to the nucleus, the distance calculated, then the distance is said to be atomic radius. As we are telling, this is a distance. It will be measured in different units like meters, centimeters, picometers, nanometers, and these all are used. Mostly frequently used units are angstroms. So we know 1 angstrom is equal to 10 to the power of minus 10 meters or 10 to the power of minus 8 centimeters. Next, however, it is not possible to measure the atomic radius directly, as an individual atom cannot be isolated. But the internuclear distance of the bonded atoms can be measured by using the techniques like X-ray diffraction, electron diffraction, and it is taken as standard. Okay, the calculation of atomic radius is a little difficult because the size of the atoms is very small. Identification of these atoms with the sensitive microscopes also a little difficult. So as the size of the atoms cannot be calculated easily. For that purpose, because we cannot isolate these atoms. So if we are able to isolate the atoms, then we can calculate their radius. But it is not which is not possible. That is why we can calculate or we can compare the sizes by considering molecular distance, internuclear distances in the between the atoms which are present in a molecule. So these can be internuclear distances can be measured by using certain techniques like X-ray diffraction, electron diffraction. Okay, by using this we can calculate the internuclear distance. So and this can be taken as a standard for calculating atomic radii. Okay, the atomic radius is measured in different ways like crystal radius, covalent radius, and van der Waals radius, etc. As we told, the atomic radius cannot be calculated directly. Just we can calculate internuclear distance between the atoms in a bonded molecule. From that, this atomic radius can be derived. But we know the molecules will be of different kinds, or the substances are because of different kinds of chemical bondings. So atomic radius is measured in different ways like crystal radius, metallic radius, covalent radius, van der Waals radius, etc. Okay, now let us see what is this, how this atomic radius varies in the groups and periods. Okay, in a period, if you see, we know the atomic size generally decreases from left to right along the period. This is because along a period, the electrons are added to the same energy level, which leads to an increase in the effective nuclear charge on the outermost shell, thereby decreasing the size of the atom. So what happens in a period? If you consider the atomic size in a period from left to right, gradually it decreases. Why? Because if you observe all the elements in a period, all they are having same number of shells, but the number of electrons in their outermost shell gradually increasing. Let us consider here the third period. If you consider third period, if I think it is second period, if you see lithium to fluorine, all these elements are having two shells only. Lithium is having two shells, beryllium is also having two shells, even fluorine is also having two shells. But if you observe for lithium, there is only one electron in its outermost shell, whereas beryllium is having two electrons, boron 3, and it is gradually increasing from left to right, isn't it? So as the number of electrons increasing, at the same time, if you observe the nuclear charge of these atoms, lithium is having only 3 units positive charge because it has 3 protons, isn't it? Yes. If you see for beryllium, there are 4 units positive charges, and for beryllium 5, and if you see for fluorine, there is 7 units positive charge. So what do we observe here? In a period from left to right, all the elements are having same number of energy levels, but the number of electrons in their outermost shell increasing. At the same time, nuclear charge is also being increased. Because of the increase in these two, number of electrons in the outermost shell and the nuclear charge, the effective attraction increases between these two, and hence the outer shell comes a little closer to the nucleus. Then what happens? Size decreases. That's why we say in a period from left to right, atomic size decreases because of the greater nuclear force of attraction on the electron cloud. Okay, generally what we may assume that as the number of electrons in the outermost shell increasing in a period from one to another, the size might be increased, we may thought. But here what in fact it is decreasing from left to right, because effective nuclear charge is being increased on the outer electron cloud, thereby the size decreases. Okay, in a period from left to right, atomic size decreases. Next, exception in this, we told in a period from left to right, atomic size increases, but there is a little exception for the noble gases, that is last group elements. What happens here? Due to their inert or interelectronic repulsions because of the completely filled outermost shell, the size is a little larger than the corresponding halogen. Okay, thus in a period, alkali metal is the largest atom while the halogen is the smallest atom. Okay, what did we say here? In general, atomic size in a group from in a period from left to right, it decreases because the effective nuclear charge increasing on the outer electron cloud. So size is being gradually decreased. But after coming to the last element in this period, that is a noble gas. As these noble gases are having completely filled outermost shell, there exists greater repulsions between the electrons in that shell. So the size increases a little. So if you see the third period itself, from sodium to chlorine size gradually decreases, and by coming to the next element, that is argon, there will be a little increase in the size. Now what we can say here, the greater sized element in a period is first group element, that is alkali metal. Alkali metal is the largest sized atom in a period. Whereas halogen, that is 7th A group element, is the smallest sized atom in a period. Okay, but not noble gases, because in a period atomic size gradually decreasing from left to right and slightly increase by coming to noble gases. Got it? So we can say alkali metal is the greatest sized element, whereas halogen is the smallest sized element. Now in a group, how this atomic radius varies in a group. On going down the group, a new shell is being added from one element to another element. As the electron is added to a new shell further from the nucleus, the effective nuclear force of attraction on the valence shell decreases, thereby increasing the size of the atom. Okay, let us consider the first group in the periodic table to understand this, how the atomic size varies in the group. If you see the first element in this first group, we say this is 1A group or alkali metals group, isn't it? Now, the first element in this group is hydrogen. How many shells are there for hydrogen? There is only one shell. If you see the next element to the hydrogen, that is lithium, it has two shells. So, the outermost electron is present in the second shell of lithium. Whereas if you see sodium, sodium has its outermost electron in the third shell. If we see potassium, it has four shells. So what we observed here, in a group, as we move from top to bottom, number of shells are being increased. So that what happens, the effective nuclear force or effective nuclear force of attraction on the outer electrons will be a little lower when compared to the small sized atoms, the upper elements which are having lower number of orbits. So as number of orbits increasing, gradually size increases. Thus we can say in a group from top to bottom, atomic size increases. Observe the size of the elements in the first group shown here, from hydrogen to cesium. What happened here? So hydrogen has only one shell, lithium has two shells, sodium 3, potassium 4. In this way, number of shells are being increased. As number of shells increasing, obviously size of the atoms also increases. It happens in all the groups. So we can say summarized, in a group from top to bottom, atomic size increases. In a period from left to right, atomic size decreases. In fact, to say clearly, from alkali metals to halogens, atomic size decreases and it increases a little to noble gases. Right? Now let us see the comparison of the size of the isoelectronic species. What are isoelectronic species? We know the species which are having same number of electrons are called as isoelectronic species. Here species representing either an atom or molecule or any ionic substance. Whatever it might be, it can be simply called species. So the species which are having same number of electrons are called as the isoelectronic species. Now, how the size being compared between among these isoelectronic species? Among the isoelectronic species, the size decreases as nuclear charge increases. For example, the size order for some isoelectronic species is shown here. Let us observe it. If you observe these all, F minus 2, O minus 2, F minus, neon, Na plus, Mg plus 2. If you observe the number of electrons in these all, they contain same number. For example, if you see oxygen, we know atomic number of oxygen is 8. It will be having generally 8 electrons. As it is having -2 charge, it represents as it gained 2 electrons. Now the total number of electrons becomes 10 for this. If we see some other, if you see for neon, we know atomic number of neon is 10, so it has 10 electrons in it already. If we see for magnesium, we know the atomic number of magnesium is 12, and it is shown here with +2 charge, so that we can understand here it lost 2 electrons, so it will be remained with the 10 electrons. In this way, these all are containing same number of electrons in them, and hence these are called as isoelectronic species. Now here, if you observe the number of protons in their nuclei or nuclear charge of these isoelectronic species, that is being different. Even though they are having same number of electrons, their nuclear charges are being different. If you observe for magnesium, we know there is a 12 units positive charge, isn't it? Yes, because magnesium has 12 protons, whereas sodium has 11 protons. And for neon it is 10 units, for fluorine 9 units, whereas for oxygen it is only 8 units. What happened? Even though these all are having same number of electrons, they are having different nuclear charges. So if you observe for magnesium, positive charge is 12 units, negative charge, that means number of electrons is only 8 units. So as a positive charge is being more, we can say it has greater nuclear charge. As being greater nuclear charge, it can attract the electrons towards it more than the remaining all. And hence, size will be less for this magnesium plus 2 ion. So simply we can say this, as the nuclear charge increases, size decreases among the isoelectronic species. That is why among these all, Mg plus 2 is having the smallest size, whereas O minus 2, because it has only 8 units positive charge, but there are number of electrons greater, that is 10 electrons are there. So size will be much for this. The greatest sized species is oxide ion or O minus 2 ion. Got it? As the nuclear charge increases, size decreases among the isoelectronic species. So it is shown here the size decreasing. Even we can write here Mg plus 2 also. Right? Size will be least for Mg plus 2 and it will be greater for O minus 2. Okay. Now let us see here the comparison of size of the anion or cation with parent atom. Parent atom means neutral atom. So and we know here anion means the ion formed by the gain of electrons. What about cation? The ion formed by the loss of electrons by a neutral atom. So when an atom loses electrons, it forms positive ions. That positive ion is called cation. When an atom gains electrons, one or more, then it forms a negative ion, which is called anion. Now, the size of the anion will be greater than that of its parent atom, because anion, we are telling anion is being formed by the gain of electrons. So when an atom gaining electrons, there exists a little repulsions between the already existing electrons and the incoming electron. To overcome these repulsions in the outermost shell, that electrons will move a little far from the nucleus to occupy maximum distance. That's why size will be bulged. That's why you can say anions are having greater size than the neutral atom. This is due to overcome the repulsions between the already existing electrons and the incoming electron. To overcome these repulsions, electrons move a little away from each other, and hence size increases. That's what is said here. The size of the anion will be greater than that of its parent atom. Now in case of cations, the size of cation will be smaller than that of its parent atom. Why? Because if you see here sodium ion, how it is formed, we are telling cations are formed by the loss of electrons. So when sodium loses one electron, what happens? number of electrons is reduced to 10, whereas its nuclear charge is maintained positive in its 10, 11. So as nuclear charge is greater than the negative charge, this greater nuclear charge attracts the electrons more, so that these electrons will come a little closer to the nucleus. Thus, size of the atoms decreases in case of cations. Okay, size of cation is smaller than the neutral atom. Size of anion is greater than that of neutral atom. Okay, it is shown here in case of fluorine. F minus is having greater size than neutral fluorine atom, whereas Na plus, that is sodium ion, is having smaller size than that of neutral sodium atom. Okay, this is about sizes of the anions and cations when compared with the neutral atoms. Anions are having greater size, whereas cations are having smaller size than the neutral atom. Right? Next, let us see lanthanoid contraction. So this is also about size variations. The study decrease in the size of the atoms and ions of the rare earth elements. That is the first horizontal row, which is written at the bottom of the periodic table. Those we call as lanthanoids also. As they are existing in the very rare quantity in the earth crust, they are also called rare earths. These are the elements. These are called lanthanoids. So, if it is observed the size of these atoms of lanthanoids or rare earths, there is a gradual decrease in the size. This decrease in the size of these lanthanoids is called lanthanoid contraction. So, as atomic number increasing, atomic size is being decreased in the among the lanthanoid elements. That is from lanthanum to lutetium. The size is being gradually decreased. This decrease in the size of the lanthanoids from left to right, that is from lanthanum to lutetium, is called lanthanoid contraction. Why it is so? Let us see. Why it is being decreased. In lanthanoids, the differentiating electron enters into 4f subshell. That is why we call these 4f or F block elements also, isn't it? Lanthanoids and actinoids are called F block elements, we know. So, why they are called F block elements? For these elements, the differentiating electron enters into last but two F subshell. That means anti-penultimate shell F subshell. So, these all are having their outermost electron in their F subshell. With increase in the atomic number in the lanthanoid series, the atomic and ionic radii steadily decreases. This is due to the dispersed shape and the poor shielding effect of 4f electron cloud. So what is happening in the lanthanides? The last electron or valence electron is being entered into 4f subshell. And for this 4f, we know the shape is a dispersed shape or complex shape. Not only that, between these 4f electrons and nucleus, as there are many electrons, these electrons will shield these outer electrons from the nuclear force of attraction. Okay, these are being affected, shielded by inner electrons, very weak. So that because of this least shielding effect, these electrons are being attracted much by the nucleus. Why the shielding effect is being less means because of the dispersed shape of these 4f electrons, 4f subshells. Because of that, attraction will be more on these electrons, and hence these are being attracted towards the nucleus. So as they are being attracted towards the nucleus, what happens? Size decreases. So the decrease in the size of the atoms or ions with the increase in the atomic number among the lanthanoids is called as lanthanoid contraction. So actually what happens in a as atomic number increases, we may expect the increase in the atomic size among the lanthanoids. But in fact, among the lanthanoids from lanthanum to lutetium, that means in the block lanthanoids from left to right, gradually size being decreased because of the poor shielding effect of inner electrons and dispersed shape of this 4f subshell. the electrons in that 4f subshell are being attracted more by the nucleus, and hence they come close to the nucleus. What happens? Thereby size decreases. Okay, this gradual decrease in the size of these lanthanoids is called lanthanoid contraction. Right? What are the consequences of this lanthanoid contraction? Okay, before that, let us see one example. The the lanthanum ion La3 plus has a radius of 1.061 angstroms, whereas the heavier lithium ion Lu, that is lutetium ion Lu3 plus, has a radius of 0.85 angstroms. If you observe the values of these two, what happened? Lanthanum he is having greater atomic radius or greater size than that of lutetium. From this we can say from lanthanum to lutetium size gradually decreasing. This is due to the poor shielding effect of inner electrons on the dispersed shape of 4f subshell of these elements, and hence is decreasing. That we are calling as lanthanoid contraction. Now let us see here what are the consequences. What is the consequence of this lanthanoid contraction? What happens by this? Due to this lanthanoid contraction, these rare earth ions exist with about same size. As there is a lanthanoid contraction, as size being decreased, almost all these rare earth atoms or the ions of these rare earth elements are existing with the same size. They all generally exhibit +3 oxidation state number, and the properties of these elements are becoming very close and similar. So because of this lanthanoid contraction, these all are existing the same size, and they all are exhibiting with the same oxidation number, means same charge, that is +3, and their properties are being almost similar. So by these all consequences, it becomes difficult to separate them from a mixture. So if you get a mixture of these lanthanoids, it is a little difficult to separate those individual lanthanide elements. Why? Because almost all they are having the same size, and all these are lanthanides are exhibiting similar properties, and hence the separation of this is a little difficult. Okay. Now let us see what is this shielding effect. We told there lanthanoids size is being decreased from lanthanum to lutetium because of poor shielding effect. What does it mean by this shielding effect? Let us see here. The electrons of internal orbits repel the electrons of outermost orbit, due to which the attraction of the nucleus towards the electrons of this outermost orbit decreases. This is known as poor shielding effect. So here, if you observe this as an atom, this is nucleus, and this is outermost orbit or outermost electrons in that, and these are internal electrons. These electrons, internal electrons, repel the outer electrons or outermost electrons, so that nuclear force of attraction on these outer electrons decreases. So this repulsion of the inner electrons on these outer electrons is called shielding effect. Okay, actually for lanthanoids this shielding effect is being less. If it is greater, size will be automatically greater, because on these outer electrons attraction of the nucleus will be decreased because of these inner electrons shielding, and hence they may move a little away because of the repulsions here. So that what happens? Size increases. But here what is happening in the case of lanthanoids, these inner electrons are shielding outer electrons very poorly because of the dispersed shape of this 4f subshell, and hence size is being decreased. Okay. So due to this shielding effect, generally atomic size should be increased. But in case of lanthanoids, this shielding effect is being very less, and hence size decreasing. So this decrease in the size we are calling as lanthanoid contraction. Okay. Thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates on recorded videos.